state to the excited state, such kind of pumping is known as optical pumping. Optical pumping matlab it has a light source. We are going to use the light as a source or the light as an external energy to take the electrons from the ground state to the excited state. We can in this you can see the your flash lamp which can use as a pumping. So that is the optical pumping, in which we are going to use the light as a pumping. Next is the electric pumping, in which we are going to use the electric discharge. So if we use the electric discharge to take the electron from the ground state to the excited state, such kind of pumping is known as the electric pumping. The electric pumping is used in our day-to-day life also, that is in the tube lights. We have two electrodes which are separated by a small distance, and when you apply the voltage across it will generate the discharge, and that discharge can excite the electron from the ground state to the excited state. And so when such kind of electrical discharge is used to take the atom or the electrons from the ground state to the excited state, such kind of pumping is known as your electrical pumping. And electrical pumping can be used whenever when you have a large bandwidth, such as your gas laser. Third is the direct conversion. When your electrical energy is directly converted into radiant energy, such kind of pumping is known as your direct conversion. Right? LED or the semiconductor laser use this kind of direct conversion pumping, in which your electron and holes recombines and directly give out the radiation. So whenever you apply the forward bias to the light emitting diode or the semiconductor laser, whatever the external energy or whatever the electrical energy which is supplied, it is directly converted into the luminous energy or the light. Right? So such kind of pumping is known as the direct conversion. Next is a chemical pumping. If the external energy is extracted from any chemical reaction, such kind of pumping is used as such kind of pumping is known as the chemical pumping. Right? Nowadays chemical pumping is not suitable or not popular very much, because every time you are going to change the chemicals also. But if you take your energy from any chemical reaction, such kind of pumping is used as a chemical pumping. Next is the indirect pumping, which is the secondary kind of pumping, in which we are going to use the one primary pumping and then intermediate atom which will collide with the another atom, and due to this collision your energy will transform from your one atom to the another, and due to which your second atom will grow from the ground state to the excited state. So this is your inelastic pumping or the indirect pumping, which is the inelastic atom-atom collision. In this pumping, one type of atom raised to the excited state via any primary pumping, that is either by the optical pumping or the electrical pumping. Your any XYZ atom is taken from the ground state to the excited state. That excited atom collide with the another atom inelastically. Inelastically collision means it has some energy loss as well as the momentum loss. So due to this collision, your energy is transferred from the one X atom to the Y atom. So due to this, your Y atom get excited. So there is a process in which your Y atom get excited, and this process is known as the inelastic atom-atom collision, which is the example of your indirect pumping. That is this. X is excited, it is collided with the Y, and it is transferred to the excited state. So this is the indirect pumping. And the last part is your optical resonators. Optical resonators are the system of the two plane or the spherical mirrors, out of which one is a total reflector which has a 100% reflectivity, and the another is a partial reflector which has a 98 to 99% reflectivity. So the mirror one has a 100% reflectivity. It can reflect all the radiation which is incident on that mirror, and your another mirror has the 98% reflectivity, so that there is a 2% of transmission. The laser pulse will come out of this optical resonators when there are certain number of photons are achieved in the stimulated process. Until then, the laser will oscillate, or the emitted photon will oscillate between the reflectors, and that's why the system of this mirror are known as the optical resonators instead of optical system. These are the two mirrors, and the active medium or your lasing action occurs in between these two. One side you have a total reflector, and another side you have a partial reflector. Now whenever your lasing action starts, your number of photons increases. Now until the sufficient number of photons are achieved, there is no output from the partial reflector. Until then, your photons are oscillating between this total reflector and the partial reflector. But whenever sufficient number of photons are achieved, you are getting the output from the partial reflector, that you can see from the red arrow. So there is that particular two mirrors are the essential for the to continue your stimulated emission. These are known as the optical resonators. Now the next part, or the next important point, is Einstein. So these are the 7 basic components of the laser. If you understand that 7 basics, you can understand the working of any XYZ laser. Now Einstein has laid down the formation or the theory for the stimulated emission. He said that whenever your external photon is interacting with the atom, your photon is absorbed by the atom, and electron can go from the ground state to the excited state. Such process is known as the absorption, and after absorption there is a two processes can happen. One is a spontaneous emission, and the second one is a stimulated emission. The process in which your electron come down automatically, such process is known as a spontaneous emission, and if your external photon make that excited electron to come down, such process is known as the stimulated emission. So now Einstein has derived the rate of absorption, rate of spontaneous emission, and the rate of stimulated emission, and from that he derived the constant which he used in your equation for this Einstein's coefficient A and B. So let us see the derivation part of the Einstein's coefficient A and B. Let us consider the two states. State 1 and state 2. State 1 has the energy E1 and state 2 has the energy E2. Let N1 is the number of electrons associated with the energy level E1, and N2 are the number of electrons which are associated with the energy level E2. Now rho is the density of the external photon which is incident on this particular atom. Now due to this, your electron can go from the E1 to E2, and via two processes, that is by stimulated emission and by spontaneous emission, they can come down. So first we are going to have a rate of absorption. Okay, when your electron goes from the ground state to the excited state, such process is known as the absorption. Now the rate of absorption is given by R12, which is proportional to the number of electrons in the ground state as well as the density of the photon, that is rho. Now if you remove the proportionality constant, your R12, that is the rate of absorption, is equal to, that is a B12 is a proportionality constant, N1 rho. Now rate is basically the number of photons or the number of electrons which are going from the ground state to the excited state in a unit time. So if we want to increase the rate, we require the more number of electrons as well as the more number of photons. So here your rate of absorption depends upon the number of electrons which are associated with the ground state, that is N1, and external photons. So as the number of electrons are more, the rate will be more, and as we increase the density of the photon, your rate will be more. So that is the first equation. R12 is equal to, that is the rate of absorption, is equal to B12 N1 rho. Now this excited photon can come down via two different processes. First one is a spontaneous emission, and the second one is a stimulated emission. So the rate of spontaneous emission is also depend upon the number of electrons in the excited state. So R21 is proportional to N1. So that is R21 spontaneous is equal to A21 N2, where N2 is the number of electrons in the excited state and A21 is a constant. So A21 is a proportionality constant. So rate of spontaneous emission is the number of electrons which are coming from the excited state to the ground state via or without any external force. So rate of spontaneous emission depends only upon the number of electrons in the excited state. If you have a more number of electrons in the excited state, your rate will be more. So R21 is equal to A21 N2. Similarly, the rate of stimulated emission depends upon it is the number of electrons which are coming from the excited state to the ground state in the unit time by external photon. So the rate of stimulated emission depends upon the two factors. One, that is external density of the external photon, and the second, that is the number of electrons available in the state E2. So your the rate of stimulated emission is equal to R21 stimulated is equal to B21 rho N2. So we have a three equation. One is the rate of absorption, rate of stimulated emission, and the rate of spontaneous emission. So if your atom is in the balance condition, the rate of absorption and the rate of emission are same. That is R12 and R21 are equal. That is R12 stimulated is equal to R21 spontaneous and R21 stimulated. So that is your rate of absorption is equal to rate of spontaneous emission and rate of stimulated emission. So if we put the value of all the three, that is rate of absorption, rate of spontaneous emission, and rate of stimulated emission, the equation is like this: B12 rho N1, that is the rate of absorption, is equal to A21 N2, that is the rate of your spontaneous emission, and this is your rate of stimulated emission. So these are equal because your atom is in the balance condition. By simplification, we can get this equation: rho, that is your density of the photon, is equal to A21 divided by B21 in the bracket N1 by N2 in the bracket B12 by B21 minus 1. So there is a equation derived by the Einstein, that is a equation for the density of the photon. Now in the population inversion, we have seen that your number of electrons associated with the any energy level is given by N1 is equal to N0 e raised to minus E1 by kT, and N2 is equal to N0 e raised to minus E2 by kT. So these are the number of electrons associated with the energy level E1 and E2. So if we take the ratio of this N1 by N2, it will come out e raised to E2 minus E1 by KT. So that is equal to your N1 by N2 is equal to E raised to h nu by KT, because your E2 minus E1 is equal to h nu. So N1 by N2 is equal to h nu by KT. So now you can replace this N1 by N2 by this value of N1 by ratio of N1 by N2. So in that we can get this, your density of the photon A21 divided by B12 B12 upon B21 into e raised to hc by lambda kt minus 1, right. So this is the equation according to the Einstein's theory. So that is the density of the photon, which is derived by the Einstein on the postulate of your stimulated emission. Now Einstein had studied the Planck radiation formula, and according to the Planck radiation formula, the density of the photon is given by rho is equal to 8 pi h nu cube by sig cube into e raised to h nu by lambda kt minus 1. So these two are the same, that is the two equations are the for the density of the photons, one which is derived by the Einstein on the basis of theory of absorption, stimulated emission and the spontaneous emission, and this is your another one that is from the Planck's radiation formula. Your rho is equal to 8 pi h nu cube by sig cube into e raised to h nu by lambda kt minus 1. So both the formulas for the density of the photons only. So if we equate this, both the formulas, we can get the values of the constants, that is A12 upon B21 is equal to 8 pi h nu cube by sig cube, and B12 upon B21 is equal to 1. So these are the constants. Now here your A12, B12 and B21 are the constants. They are the proportionality constant. So in general we can have A12 is equal to A and B12 is equal to B21 is equal to B, because here the subscript 1 and 2 shows the direction of the electron which are going from